Hello, everybody. I think the webcams are loading for the audience. Hi, welcome. Thank you so much for being here and joining us for our fourth installment in our webinar series, Electrochemistry in the TEM. My name is Jen McConnell. I'm a product manager here at Protochips. And today we have a wonderful speaker who is going to present in our first webinar surrounding the study of catalyst materials using our Poseidon electrochemistry system. And of course, others analytical techniques that will complement these results as well. The last webinar had a similar focus, but surrounding battery materials. And previous to that, the first two webinars were surrounding the considerations and methodologies for performing quantitative nanoscale electrochemistry. And what do you need to think about when you are miniaturizing a standard electrochemistry experiment? So you can find those on our YouTube page. Feel free to reach out to us also via the webinar email that you got if you've got any questions about that. And I know I've mentioned this before if you've been on these webinars, but we're so honored to host this series because it means Protochips users are some of the most experienced liquid cell TEM researchers in the community. Many of them have been using this technique for 4, 5, 6, 7 years, which makes them excellent mentors to learn from. And our speaker today is absolutely no exception to that. So feel free to sign up for as many webinars in the series as you'd like. It's at protochips.com/webinar. You'll see it in the chat box as well. And we'll be posting registration links for the next set in the spring and summer very shortly. So a couple housekeeping items before I hand this over to the star of the show today. Everybody in the webinar is muted today. It's just too large of a crowd to have everybody kind of unmuted at once. So any questions you have, please enter them into the questions box, and we will do a Q&A at the end. And then if you wouldn't mind filling out our survey that pops up at the end of the webinar as well, we would greatly appreciate that. Okay, so let me tell you a little bit about our speaker, and then I'm going to hand it over to her, and she's going to take it away. So our speaker today is Dr. NATHALY Ortiz PEÑA. She's a chemist from the Université del Valle in Colombia, and she completed a master's in nanoscale engineering at INSA de Lyon in France. She then moved to Strasbourg to develop PhD research at IPCMS de Strasbourg under the supervision of Professor Ovidiu Herein. Her primary work performed during her doctoral research was framed in the implementation of a liquid cell for transmission electron microscopy to study electrocatalysts in operando. Now, beyond electrocatalysts, she also studied a variety of other materials to understand their formation and degradation mechanisms, including systems such as iron oxide nanoparticles, calcium carbonate, and other biominerals. As her first postdoctoral experience, she was able to identify that the electrodeposition of pyrocatechol from solution produces thin films of graphite oxide, and the complete comprehension of such a process required the articulation of a correlative approach, combining liquid cell TEM with other microscopy techniques such as scanning transmission X-ray microscopy and atomic force microscopy. And since then, she's decided to join the MEANS team under the supervision of Damien Allouet at MPQ and the Université de Paris. They have implemented a complementary approach by using in situ liquid phase transmission electron microscopy, ex vivo TEM studies, and in vivo biological analysis to unveil a new aspect of the behavior of molybdenum disulfide patches in cells. So currently she works at the Paris Globe Institute of Physics in collaboration with MEANS to study the feasibility of living organisms observation within the TEM by analyzing de novo. So an impressive background. NATHALY, thank you so much for being here. I'm going to pass it off to you and look forward to seeing your results.
Thank you so much, Jen, and thanks to everyone who have joined. And as Jen was mentioning, I'll be talking about my PhD work mainly. That was the one was involved in electrochemistry using the Protochips setup, and the main example that we have used, which is cobalt oxide. But I will also mention a little bit about our posterior work about the electrodeposition and correlative techniques. So I like to start by talking a little bit about what is electrocatalysis. I guess if you are interested in this series, you might already know about this concept, but for those of you who don't know or not familiar, electrocatalysis refers to the acceleration or the catalytic acceleration of an electrochemical reaction that happens at the surface of an electrode and involves charge transfer. And this subject of studies, it has unveiled a lot of interest because it's the center of the energy transition, which is very important nowadays, because whether it's to store or to convert energy, the reaction happen at the surface of an electrode. And the reactions that are more important are the oxygen evolution reaction, the oxygen reduction reaction, or the hydrogen evolution or reduction reaction. And these are key reactions to really take to the next level the use of devices like fuel cells or other devices to store or convert energy without producing any damaging subproducts. But the choice of the electrocatalytic material that we have to do needs to limit the amount of very expensive materials. So typical electron materials are platinum, palladium, ruthenium, which are scarce and expensive. And other types of materials start to be studied, like materials that have oxides of transition metals and other types of metals. And the activity will be related with different aspects, including the structure, the support in which it's used, the shape, the polymorphism that are used, the interaction with the absorbates or other morphological aspects. And different strategies have been developed to try to increase the performance of these materials, including the increase of the active sites by decreasing the size, so using nanocatalysts, for example. But this also always tends to get to a limiting point where transport limitations are too important to attain the theoretical performance. But then what would be really useful is to increase the intrinsic activity of the material. And to do so, we need to understand what is the mechanism of electrocatalysis. And of course, if we want to understand this, we need to understand what type of process and where they take place. And actually, we look at the electrocatalysis, it will take place at the surface of the electrode, but most importantly, at the surface of the catalyst. This surface is typically only few nanometers thick. And we will need to understand also if these reactions are reversible or irreversible, because that might lead to degradation or deactivation processes. And more importantly, that the interface at which this reaction happens are typically solid liquid, because our materials are solid and our electrolytes are liquid in the case of fuel cells, for example. So this is where the TM have an important role, of course. And what we want to see is what happens at potentials that are relevant for our reaction, meaning that we want to decrease the over potential that is applied to drive the reaction. Typically do by cyclic voltammetry, for example. We are able to observe how the current changes with an applied potential, and we want to minimize the amount of potential that we need to apply. And in previous study has been shown that morphological changes can take place in materials like cobalt oxide, which is one of the most studied materials currently. And we were attracted by this material in order to use it as a model system to compare with other operando techniques that have been already done in the material. And as I will show you, the model material sometimes show things that we are not expecting maybe. And this led us to the choice of the TM as the technique of choice, because it allows us to, and thanks to the new setups that allow us to enclose a really thin film of liquid and having a really thin electrode, we can see how the electrocatalytic material behaves upon cycling at the nanometric scale, meaning that we have real time and space observation with the application of an stimuli, like in our case, an electrochemical potential, for example. But of course, there are challenges when we are inputting an electron beam within a liquid in an electrochemical media. So we had to answer several questions regarding how the sample should be prepared, which type of imaging mode should we use, how the resolution would be degraded with the amount of liquid we would put, which electron dose should we use to avoid any electron beam damage, and how to perform post-mortem analysis in samples that are not the typical ones. So most of my work during my PhD was precisely related to how to answer to all those questions and regarding the electrochemical TM. So I will explain a little bit later, a little bit more about the setup, but this gives us already an idea of how our cell is constructed. So we have two silicon chips that have a silicon nitride window, in which there is one that has imprinted an electrochemical circuit down where we have an electrode of glassy carbon, and where we can, which is electron transparent, we can put our catalyst. And this is connected to a potentiometer out of the holder. And we can see through this silicon nitride window our material in contact with an electrolyte. So the different things can happen, as I was telling, due to the interaction between the beam and the electrolyte and the material, the formation of bubbles or the radiolysis products, also the effect of the flow within the chamber. But we try to overcome all of that to observe material. And I think it is important to take into account that this setup, of course, will be different from a classical electrochemical cell where typical materials are tested to evaluate precisely that over potential that they can present. So a typical electrochemical cell is composed of a reference electron, a working electrode, and a counter electrode. And in our case, the material were analyzed by a glassy carbon disc in a rotatory system. And we have an electrolyte that could be adapted depending on what we were interested on. In our case was a basic electrolyte, which is potassium hydroxide. And we tested the silver chloride reference electrode, which is the, let's say, most used reference electrode. And we also tested platinum wire as reference electrode in order to be able to compare with our electrochemical cell in situ. So as I was mentioning before, thanks to the holder of prototypes, we have a miniaturized electrochemical cell where we can have a working electrode of glassy carbon, a reference electrode around out of the observation window made of platinum, and that's why we try to do our experiments ex situ as well with a platinum reference and a counter electrode of platinum as well. And we are able to pass through the two windows the electrolyte and connect everything to a potentiostat and do the electrochemical measurements while we observe our material. So, of course, I mentioned it before, there is a number of things to take into account in order to have representable data once you do your observation. So there are three things that we need to take into account: that the imaging parameters are good enough in order to be able to observe something, right? That this data is representable, that it actually corresponds to what the processes ex situ could be, and that the electrochemical window that we are using is also representative of that we would use in a typical cell. No? So we try to optimize all of these parameters throughout our experiments. We show you some of the things that we took into account. One was the sample preparation. Classical ink for an electrocatalyst testing would be the particles. In our case, cobalt oxide, but most of the electrocatalytic materials, especially in nanoparticles, will be tested in this way as well. With a carbon active material that will allow the percolation of the electrons. In our case, was carbon black. Naphthalene that will be used as a polymeric material to keep everything in place, and in this case ethanol to disperse everything. This will allow that the particles keep being in the surface of the electron and don't go away upon rotation when we are doing our experiments. But in our case, we wanted to limit all the sources of interference when we are looking within the microscope, because things like naphthalene can degrade under the beam. The black carbon, for example, can bring another image into our observation that we would be able to differentiate from the cobalt oxide, for example. So we wanted to make sure that we were looking only at the cobalt oxide. So we tested inks without any carbon black or naphthalene, only the nanoparticles, seeing what was the addition of the particles. And we were able to show that even upon 100 cycles of only nanoparticles in ethanol, they remain in the surface of the electrode. So we thought that this this means that we are able also to do our experiments without any other additive and be able to observe only our nanoparticles. So for the in situ TEM, we use only the nanoparticles deposit on the surface of the electrode. But second thing is, when you put your sample, you just cast a drop and it will go all over the chip. And of course, that might create some short circuits, or it will spread all over, and we wanted to limit that. So for that, we create a mask that allow us to put our sample only on the surface of our window. And this allow us to make sure that there were not that the current that we were measuring was coming only from our window. I know that nowadays there are very specific techniques for the sample preparation, where they use micro sampling to put specific amounts over the electrode. This is what we had at the time. We figured out a way to put it only on the window. After that, we thought, okay, what type of imaging mode should we use, TM, STM? So we tested both. Of course, both will give us different advantages and disadvantages in terms of imaging. If we use TM, we would be able to focus more on the particles at the bottom of the chip. For STM, more of those at the top of the chip. Besides that, if we use TM, we see that there is a strong influence on the electrochemical behavior on our sample due to the, of course, the high influx of electrons coming from the TM mode. So that we don't observe in STM mode. So besides the fact that we are able to focus more on the top window, which is the one where are the nanoparticles, also the fact that we don't observe any interferences from the STM mode on the electrochemical behavior led us to use this imaging mode. So other things to take into account that it will be also a question not only for material scientists working on electrochemistry, but for anyone who is interested on electrochemical behavior, it is what the effect of the beam on both our material and the reactions that we are observing. So one of the very important things when you are doing your experiments, I think, to take into account is to evaluate the beam damage induced by your beam. And we tested different spot size. And what we observe is that depending on the spot size that you use, of course, you will have better or worse resolution. But also it will, prior to any beam-induced transformation, the particle will detach because of the accumulation of charges at the surface of the observation window. So in our case, in particular, they won't degrade because of the beam, but they will go away from the window. So if we use a very low a very low electron dose beam current, the particle will remain longer times on the observation window. But of course, the resolution would be worse. And if we use very high doses, we will see the particles better, but they would go very short times. So we decided to use an electron dose that will allow us to enough time to see our particles, but without degrading them or making them go away. And this is for this particular case, but in other cases, your beam can induce changes on the materials that you are observing. So it is very important that you evaluate this electron beam effect. So as I mentioned before, we have a platinum reference, which is known not for being the best reference because there might be shifts on the electrochemical potential upon cycling or upon changes on pH. So at the time, the best solution that we found was to use an internal reference, which means that we use a redox couple that it has a known electrochemical shift, and we put it in our electrolyte solution, and we tested both ex situ and in situ, and shift the signal with respect to this electrochemical reference. So ex situ with our reference, we see that the ferricyanide within the KOH electrolyte, 0.1 molar, has a 1.2 volts with respect to the hydrogen electrode. And we test our material well without the internal reference to see that there is not there is no effect of the reference in the electrochemical behavior, only measuring the signal. We test within our system the same particles without any reference and without the reference, and we see a certain shift, and we are able to shift all our signals with respect to the internal reference. So we know that we are working in a certain potential window, which is very important for certain systems that might degrade at higher potentials, and that might undergo different processes depending on the potential window that we use. So this is the strategy that we found, but I think maybe Jen will talk a little bit about it. But I know Protochips is working on having what we would call a real reference, and we are excited to see how is that gonna go. So once we are sure that we are working in the potential range that we wanted to work, we can start our experiments. So first thing that we could do was to observe our materials and in a dry state, meaning only deposit over the electrode. They had a size between 12 and 15 nanometer, more or less, are nanoparticles. Then first thing that allow us our system is to see if the interaction between the particles and the electrolyte induces any immediate changes, to say it somehow. And we didn't observe any changes, at least in terms of the general morphology and the size of the nanoparticles. So the electrolyte doesn't change significantly, or nanoparticles, but it also allows us to see in situ that upon 25 cycles, the overall size of the material seemed to have decreased towards 5 nanometers or so. And we seem to have two different contrasts. And this leads us to think that there is different densities on the material. Since we didn't use any additive, nor carbon black, nor naphthalene, we know that what we have here, it must be our cobalt oxide. So we are sure that we are seeing still cobalt oxide, but so what is happening is the cobalt going away? Is it changing? What do we have in our media? So in the liquid, we know that something is happening. And now what we can do is to take our sample and observe afterwards what is happening, and see already if this change is permanent or not. So what we were able to track in situ, and was a very exciting day, was the day when we did this video. So we have our particles, we see a layer that goes away, retracts again towards the particle, and grows back again upon cycling. So what we think we are looking at is the amorphization of the surface of the cobalt oxide, which has been, as I mentioned before, already observed or determined by excess measurements, but has never seen before in direct like we are seeing here. Just one little last time of this really nice video that I liked very much. And then, okay, so is this a real amorphous layer, or how is our material changing? So what we did was to compare our pristine material, which of course is composed uniformly of cobalt and oxygen, sorry. And then particles that we recover from the surface of our electrode. Actually, we observing them directly on the surface of the electrode, and we see that there is very small crystallites, and there is an amorphous matrix around it. And when we do the ADX, we are able to see that this amorphous layer is still composed of cobalt and oxygen, meaning that our cobalt didn't go away, at least not completely, but mostly amorphized and some of the crystalline parts, of course, decreases in size because of the amorphization. Next thing that we were able to do was to test how far this amorphization can go. To do so, instead of cycling the potential, we fix a certain current and we observe how the potential changes and what is happening on our material while this is happening. So we see our particles changing in form. This overall mushroom, I will repeat it, increases in size, and the most contrasted parts mean that are crystalline particles, and the rest of it becomes amorphous. The overall change of this agglomerate is an increase of the size of around 8%, which means that the amorphous layer, of course, takes more space than the crystalline part. And what we were able to see is that after a certain point, there is no more amorphization. The amorphous crystalline matrix remains more or less the same, and the crystalline particles remains within this amorphous matrix. Another important thing to mention here is that there is no the electrocatalytic activity doesn't decrease because of this amorphization. It just keep working. It keeps acting as electrocatalyst. So this might be an activation stage of the material, which is, for example, cobalt phosphide has been known to go through this amorphization to activate. So as I mentioned before as well, we wanted to make sure that there is no beam effect on our materials upon observation. So one of the amazing things about electron microscopy is that we can do various different tests regarding the structure and the morphology and the electronic structure of the material. So this is what we do here. We test our material as prepared, and the ratio of the L peak in a regular cobalt oxide is around 2.8 because of the ratio of cobalt 2 and cobalt 3. When we put our electrolyte and we only irradiate with the beam, we observe a shift of our material towards 2.6, meaning that there is no beam induced changes, only a little bit of shift of the peaks. Then if we test what happens up after 2 hours of chronopotentiometry, we see there is a big change of the ratio of cobalt to cobalt 3, inducing a reduction of the most of the cobalt 3 to cobalt 2, forming this probably cobalt oxide, which might be the small particles, but also cobalt hydroxide, cobalt hydroxyoxide, and that is present in the amorphous way. And this tells us that these transformations are induced because of the electrochemical activity and not because of the beam irradiation. Another important thing that we were able to show was that upon cycling, as we mentioned, the crystalline phase changes in a basic electrolyte from cobalt oxide spinel to cobalt monoxide, cobalt hydroxyoxide, and cobalt hydroxide. And we have very small crystallite size, and we have the amorphous matrix, which is not exactly the same as when we use buffered phosphate electrolyte, as we did in this case. So we did the same experiment with these different um, electrolyte, and we were able to see, again, if we do chronoperimetry, meaning imposing a certain current to push the reaction, we will find again a small crystallites, and we could even find the layered structure of cobalt hydroxide. But if we do cyclic voltammetry, we don't find the small crystallites, but rather a very small layer of cobalt hydroxide and in general cobalt oxide, meaning that this reaction in this solution is probably more reversible than in the potassium hydroxide. So we were wondering if this is only a pH effect. So we decided to test a different neutral pH electrolyte, like KCl. And what we observe is that in the case of KCl, we don't see amorphization. We rather see an extended crystallization of the surface, and leaning more towards the formation of monocrystalline surfaces, different from what we would see in the previous case. And we have different phases composing, mixing within the same material, but no amorphous layer was found. So there is definitely an effect of the electrolyte on the amorphization process. So we were very happy to be able to observe on direct the amorphization of the surface of cobalt oxide. Of course, all of this required the optimization of the in situ observation parameters. And we think that we point towards the idea that the amorphous phase is the active phase, probably, which is not an unknown idea for the electrocatalyst community. And we think that here we show that this might be probably an activation stage. And we show as well the effect of the electrolyte on the process. This work has been published in ICS Nano. I wanted to show you a second example, which is not really related to electrocatalytic materials, but rather to the deposition of electroactive materials on the holder. And I wanted to show you this because this shows the versatility of the things that we can do, not necessarily purely in situ, but only with the idea of having an electrochemical cell where we can do TM afterwards or during the process, and that we can also translate that to other techniques. So in this case, we were interested on what happens after we cycle the potential of an electrode within an aqueous solution of pyrocatalytic, which is the molecule that I have here. This induce an oxidation, a reduction. We thought the Professor Vincent Val from the University of Strasbourg observed that there was a decrease in the current upon cycling. And we observed when we scratched the surface of the electrode that we were able to recover some grains of this electrode deposition film. And we found that all of it was formed of carbon and oxygen, but there were some patches with different contrast from the rest. And there were some regions that were definitely crystalline, meaning that we are forming something that is composed only of carbon and oxygen and has crystalline structure. So we wanted to see what was happening. This was an indication that probably we are forming a graphitic structure, and we wanted to test this idea. So we used the electrochemical cell to electrodeposit the pyrocatalytic. So we pass through our solution of pyrocatalytic, and then we cycle the potential and see what was happening at each state. This is in dry conditions, so we remove every time the chip and observe what happened upon cycling. So at the beginning, we right away observe the formation of structure that has some crystalline regions, but there is a polycrystalline characteristic to it because we can see rings of this material. If we continue cycling, we are able to find again the same patch, and we see that these crystalline spots start to become more and more clear and go towards the monocrystalline structure. And that's what happens towards 8 cycles. And we effectively see the decrease of the current during the cycling, which means that the structure that is forming is less electroactive than our electron material, and which would go with the idea that we are forming carbon graphite oxide material. And this slide allowed me to talk about a little bit identical location TM, which is a known technique for electrochemists that typically use grids of TM, put them close to an electrode to their experiments, that remove every time their TM grid and observe. We can do the same thing with the miniaturized cell, find at different times of the experiment the same particle or the same patch or the same region to evaluate different points on the reaction, which is not exactly operando, of course, but allows to have a track of different points of a process, no? Another thing that this allow us was to observe that effectively upon several cycles, like 25 cycles, we form a film on the surface of our electrode, but more so beyond the electrode, which is probably related to the fact that the material is also electron conductive, so the reaction can take place also far from the electrode. And if we do correlative atomic form microscopy to see what is the thickness of the material deposit, we see that there is a layer around 10 to 15 nanometers on the film, meaning that probably this is not a single layer material, but a stack of different materials that prefers to spread away instead of keep stacking on itself, because the uniformity on the material is quite extended. Another correlative study that we were able to do was the scanning transmission X-ray microscopy, which is a highly resolved spectral technique that is used, is performed, in this case was performed in the synchrotron of Soleil in Paris. And this allows us to have excess spectra at each pixel of the image and correlate this with optical, an electron image, for example. And we were able to see that the different ratios of carbon and oxygen throughout different regions of the the electrodeposited film, and that this material it has effectively carbons that would correspond to graphitic materials that we have been thought we're thinking at the moment. So this shows the power of using the exact same sample with different techniques, because this is the exact same chip that we took to the synchrotron and observed with the different techniques. So in this study, we finally showed that we are able to produce graphite oxide in really mild conditions from a simple organic molecule, which is a very good thing, but more so that we could use this system to do correlative approaches. For example, in this case, using TM, XTXM, and AFM to create a more complete picture of what is happening in our reaction. And finally, I would like to show us a perspective. This is really like the idea, even from the beginning of my PhD, is that the importance of using different operando and in situ techniques to complement the different studies that we perform, because in situ TM give us information about the morphology, the crystallographic phase, the chemical distribution, the electronic structure at the atomic or particle scale. But in situ X-ray analysis can give us crystallographic, electronic, and oxidation state at the macro scale in a very local environment. So I think this really complement each other, and it is important when doing any operando study that we are able to make sure that what we are looking at is really representative of what is happening in a typical cell. So I think that's the future for the not only the in situ TM, but for all the operando techniques at the synchrotron or in situ Raman, in situ IR, etc. So thank you so much. Sorry, this is a mistake, not at Strasbourg anymore. But yeah, yeah, that's it.
Thank you so much, Natalie. That was great. And I can't agree more with the importance of complementary techniques to fulfill the whole story of what you're trying to tell. No research is really based on only a singular technique. The story comes from the multiple sides all put together into a final picture. So I couldn't agree more. So a handful of questions. So let's start going through these. And if we feel we're running short on time, I may just connect you with the asker of the question, and maybe you could reach out to them to help them understand the answer if you don't mind. But let's go ahead and get started. So the first one says, thank you for your talk. I have a question regarding your beam influence studies on CV cycling. Did you perform STEM and TEM at the same electron flux density and same irradiated or projected area?
Well, it is difficult to say that same electron flux density, because TM has a parallel beam while STM has a convergent beam. So it is in the same area, that's for sure, because we were in TM, we were in STM, we did the experiment, and then we passed to TM, keeping it in the same place, and we just switch the mode and do the measurement. About the electron dose, I think that for TM will be higher for sure, but it would be interesting to keep it as low as possible to be able to compare with STM. Probably, sure, we didn't think of that at that time. Yep.
A short plug, because I can't help it, but our new axon dose module may actually help with these types of studies in the future, where it quantitates the flux and the accumulated dose in STEM and TEM using a Faraday cup picoammeter and creating a calibration profile for your TEM instrument, so you don't have to calculate it anymore. So Yeah, if anybody
Yeah.
is curious about that, let us know. Okay, so next question. Did you not see any impact on the OER activity from adding the ferrocyanide as an internal reference in the electrolyte? Since cobalt iron catalysts are much more active than cobalt only catalysts, are there any other internal references one could use?
Yeah, thank you for this question because I think we observe when we cycle for a long time, the potential start to shift towards lower potential, meaning that the over potential is decreasing. And at the time, I was thinking, wow, we are improving the electrocatalytic activity, and then I understood that it is due to the ferricyanide. So when you don't put it, of the electrocatalytic activity keeps stable, and it does have an impact on the electrocatalytic activity if you cycle for a long time. With the amount of material that we use, might be a few hours of the experiment. Maybe in a big reactor, it might take longer, but for us, the times are different than in a regular reactor. But yes, so for the final experiments, we try to not use the internal reference, since we saw that when we don't use it, and the potential is more or less the same that when we use it, and we just wanted to make sure that we will keep on that window of work, and we use the onset of the electrocatalytic activity as a reference in that moment when we don't use the internal reference. Yep.
Great. Okay, let's do it's like more questions keep coming as you're talking. So let's do a couple more and then I'll connect you with the rest of the questions to reach out to them privately. Again, thank you for this great talk. Did you observe a dependency of the electrochemical response on the thickness of the liquid layer?
We didn't measure the liquid thickness. We only could use the parameters that we could handle, right? Like the electrolyte flow and the spacer that we could use that was minimum 500 nanometers because of the electrodes. So we try to use always the same parameters, but I wouldn't say that we control the thickness of the liquid in order to verify that this thickness would change the electrocatalytic activity. But I would say that the times that we could see better, of course, is when we had bubbles. So I would say that in those cases, the thickness would be smaller, but we didn't see an impact on the electrochemical signature, for example. So I don't think if you don't go beyond a certain small thickness, that would impact too much on the on the electrocatalytic activity. But you need to use more or less the same condition that you would use in Situ, for example, saturating your electrolyte to make sure that with the outcoming flow of the electrolyte, you would keep all the species that you need available for the electrocatalytic activity to take place. One, and second, finding the good scan rate for the cycling, for example, because the depletion of species might happen faster than in a regular 3-electrode cell, of course. So if you go too fast, everything's gonna go away. So those are things that need to be taken into account, probably. Yep.
Great. Let's do one more, and since we're a little over time, and then we'll get you connected with everybody to answer the rest. Really nice work. In the electrolyte comparison slide, maybe slide 19, they suspect, did you do any quantification of the cobalt in solution afterwards? Structural changes might indicate dissolution and counterions, such as chloride and sulfate, which could have significant impacts on the resulting structures after cycling.
No, unfortunately, no. Thank you for this question because I think it's definitely another thing to add to the list of wishes that we would like to have. And I know that, for example, Arnaud de Mortier have started doing some steps towards that, recovering the electrolyte from reactions. We should definitely do that. We would need really sensitive after mass spectrometry to be able to determine, because the amount, if we recover the samples from our in situ setup, of course, which will be very small compared to a 3-electrode cell, but that would be something that we would like to do, of course, to prove that the metals are not leaching away on the solution. And I think it is, as Arnaud have done, and I think it's not that difficult to just recover your electrolyte and then go and test it. But things like the sample deposition would need to be really optimized as well in order to be sure that everything is touching the electrode, that is not something that is going away on the flow just because it's not well attached, things like that, right? So that's the little nuance. The only recovering the electrolyte might be not enough, but it's something that we need to definitely think about as well. Yep.
Great. I'm going to go ahead and wrap it up here. There's like 8 more questions, but I'll send them to you, Natalie. Natalie,
Sure,
thank
no
you
problem.
so much. That was a fantastic presentation. Please, if you haven't signed up for the rest of the webinars in the series, please go to our website to do so, and we'll be posting this on YouTube shortly. Thanks for joining, everybody, and thank you again, Natalie. It was fantastic.
Okay, thank you. Bye.
Have a good day. Good night, everyone.